Welcome back. This is the last lecture for Unit 1, Chapter 2. And we're going to be putting things together. We're going to be relating all these molecular forces that we've been talking about, and we're going to relate them to the chemical and physical properties of different substances. And in your textbook, it's page 75 to 79. And so by the end of this lecture, you'll be able to relate temperature change, melting point, and boiling point to the intramolecular forces and intermolecular forces found in a molecule or in a group of molecules. You'll be able to relate the mechanical properties of solids to the forces inside the molecules of those solids. And you'll also be relate the idea of conductivity, or the ability of a chemical compound to conduct electricity based on the type of forces that are inside that compound. So first we'll start talking about states of matter. The state of an element depends on the strength of attractive forces between the particles in a sample of that element or compound. In terms of changing states of matter, the intramolecular forces that we can find in a molecule are ionic bonds and covalent bonds, depending on the substance. There's also the intermolecular forces that hold molecular compounds together, and those are the dipole-dipole forces, hydrogen bonds, and London dispersion forces. So in solids, the attractive forces between particles are strong. So the particles do not have enough kinetic energy to break the bonds, and the bonds that need breaking depend on the substance we're talking about. If it's an ionic compound, then we've got to break ionic bonds. If it's a molecular compound, then we got to break intermolecular forces. In liquids, the attractive forces between particles begin to weaken. The particles have enough kinetic energy, or enough ability to move, so that they break bonds, but they're continually forming new bonds. And finally, in a gaseous state, the attractive forces between particles are completely absent. Each particle in a gas is so far away from every other particle in that gas that they're not attracted to each other, and even if they do become close to each other, they're moving so fast that there's no chance for that attractive force to slow them down and make them stick together. They're moving so fast, the attractive force between them is negated. When we're changing state, there's some words that we need to use, so some definitions. Kinetic energy has to do with the motion of particles. Particles with lots of kinetic energy are in rapid motion. Particles with a little bit of kinetic energy are slow-moving particles. And so the amount of kinetic energy in a sample of molecules is directly related to the temperature of that sample, the temperature that we would measure in Celsius, degrees Celsius. The warmer the sample of molecules, the faster those molecules are moving, the more kinetic energy they have. When we're changing states, it's called a phase change. So when, for example, ice melts, it's going from a solid to a liquid, so that's a change in phase, a change from the solid phase to the gas phase. And during this time, the temperature of the substance does not change. So you can have ice at 0 degrees, it melts, it becomes water at 0 degrees. Its temperature doesn't change, but the kinetic energy of its molecules must change, or so what that means is the kinetic energy of those molecules also doesn't change. It's just being transferred to a different type of kinetic energy. So the temperature at which a substance changes from solid to liquid is called the melting point. The temperature at which a substance changes from a liquid to a gas is called the boiling point. And the energy associated with these changes are called enthalpies. So when you change 1 mole of a solid into a liquid, a mole is just a number of atoms. We'll be talking about that actually next lecture. It's called an enthalpy of fusion. So fusion is going from a solid to a liquid. And going from a liquid to a gas is called vaporization. So changing 1 mole of liquid into a gas is the enthalpy of vaporization. So, and the way we view state changes is, in a solid, as particles gain kinetic energy, they begin to vibrate faster. So in a solid, particles are close together, they're vibrating, they're bouncing off just their neighbors. Once they get enough kinetic energy to vibrate fast enough, they start breaking bonds between immediate neighbors. So they vibrate to a point where they vibrate so fast and so strong that they can actually pop out of place, and it would be on the edges of the group of molecules first. They'd move a little, but when they do that, they lose just enough energy to have to fall back into place and form a new bond with a new neighbor. Again, they gain energy, they break a bond, they move a little, form a new bond, etc. And then as this happens, the substance then enters the liquid phase. If we keep adding energy to this sample of element or compound, the molecules are going to vibrate even faster. So they start becoming fluid, and so they break a bond, they move a great distance, and they don't form new intermolecular bonds. So if they don't form those intermolecular bonds, they can start entering the gas phase. If there's still bonds between particles, then you're still going to have a liquid. They're still going to be grouped together. They're just fluid. If they get enough energy that they start breaking those intermolecular bonds, they enter the gas phase. In the gas phase, molecules are almost completely unaffected by intermolecular forces because they're moving so quickly and because they're so far apart. So depending on the type of substance, we need to look at what these forces we're talking about, or these bonds we're talking about. We have to figure out what needs to be broken. So when we look at metals and alloys, metals and alloys only have metallic bonds. They have those positive ions surrounded by a sea of electrons. And so when we melt this, what we're doing is we're actually loosening up those positive ions, and we're actually making those electrons spread further out. So the bonds that have to be breaking would be just the metallic bonds. So they're the only bonds holding metals together. When we look at ionic bonds, ionic compounds consist of two types of statically charged particles. Positively charged particles, the cations, and negatively charged particles, the anions, and they're attracted to each other. So in order to melt or boil an ionic compound, you have to be able to separate ions. So the bond you're breaking is the ionic bond. For molecular compounds, now molecular compounds contain a bunch of bonds. They have covalent bonds, London dispersion, dipole-dipole, possibly, if they're a polar molecule, and hydrogen bonds, if they have specific atoms. So a molecular compound, when it melts or it breaks, the covalent bonds don't break. So the bonds that are holding atoms together don't break. So when hydrogen, for example, hydrogen gas, it's a gaseous substance. It consists of a bunch of discrete molecules. Each molecule contains two hydrogen atoms. But London dispersion forces, the dipole-dipole forces, and hydrogen bonds, those are the bonds that are responsible for keeping molecules together or spreading apart. So the bonds we have to break are those three bonds: the London dispersion, dipole-dipole, and the hydrogen bonding. So for metals and for ionic bonds, we notice that there are some patterns, especially if we look at our periodic table. We've noticed that all metals and all binary ionic compounds are solid at STP. So metallic compounds and ionic compounds are all solid at STP, which means they have fairly strong forces holding particles together. At standard pressures, all metals and ionic compounds melt at temperatures well over 100 degrees Celsius. Most of them don't start melting to at least 181 degrees Celsius. For a lot of the metals and even for a lot of the ionic compounds, you have to get into temperatures of the thousands before they actually melt. If we look at their boiling points, again, their boiling points are very, very high, well over 1,000 degrees Celsius to boil metallic or ionic compounds. And this is the idea of trying to boil, say, a sample of iron. Iron doesn't boil until you get to extremely hot temperatures. Its boiling point is actually on the periodic table. So if you look at something like iron, it doesn't boil until 2,861 degrees Celsius. So very, very hot temperatures to break metallic bonds and ionic bonds. And so that's the message you want to be taking from this, that metallic and ionic bonds are strong bonds. If we take a look at molecular bonds, most molecular compounds, especially the diatomic ones, are gases at STP. So most of them boil at relatively low temperatures. Most of them start to melt below 100 degrees Celsius. So between 150 degrees to minus 259. So they have low melting points. They also have low boiling points. Most of them have boiled under 200 degrees Celsius. You've boiled just with every diatomic molecular compound. So what this means is that the intermolecular forces are weak forces, and we said that before. So these forces are weak. Ionic and metallic forces are stronger. Still note that covalent bonds still haven't broken. When you boil and melt molecular compounds, you haven't broken the covalent bonds. The molecules are still held together. In contrast, when you boil something that's ionic, you're actually causing ions to separate. So you actually end up with positively charged particles and negatively charged particles basically being separated from each other. And that's why it takes so much energy, such high temperatures, to separate those statically charged ions. The covalent bonds are still not broken, so covalent bonds are still strong. They're actually stronger than metallic and ionic bonds. And so from this we can say that ionic and metallic bonds are stronger than London dispersion, dipole-dipole, and hydrogen forces. And in terms of those intermolecular bonds, the hydrogen bonds is the strongest of the three. If something has hydrogen bonding, it greatly increases the melting and boiling point of the substance. And so what we can do is I'm never going to ask you for specific numbers for compounds, but what we can do is by recognizing a compound, what type of compound it is, we can order them in terms of melting point and boiling point. So here we're going to organize in terms of boiling point. The question will work exactly the same way in terms of melting point. It would be exactly the same order. If something has a high boiling point, it's also going to have a high melting point. And so what we're going to do is just classify substances. So here we go. NaCl is ionic. C3H8 is molecular. C2H5OH is also molecular. Si2 is molecular, but it's one of the ones where we have to remember that it's a network solid. And the last one is also molecular. Once we have identified those, so here's what we can do once we've identified that. We know that sodium chloride is going to have a high boiling point, and silicon dioxide is also going to have a high boiling point because it's a network solid. This is, remember, all covalent bonds joining molecules. So, and if there's no intermolecular forces, it's very similar to an ionic compound in terms of how all the atoms are joined together. So now that we have those two, we know that these two are actually going to be the ones with the highest boiling point. Now we're going to go back to our compounds and take a look at what other forces they have. So our molecular compounds all have London dispersion. If we take a look and draw Lewis structures, and I'm going to cheat just a little bit here for Lewis structures. Here I can see this is vinegar, or not vinegar, sorry, this is ethanol. It has the OH at the end, which means it's going to have hydrogen bonding. If I take a look at this molecule over here, notice that I have 2 carbon center, but I'm going to end up with a chlorine on one of those carbons. So this one, this particular molecule, is going to have dipole-dipole dipole forces. This C3H8, and especially for all of these compounds that contain just carbon and hydrogen, they're all non-polar. They just contain carbon and hydrogen, so there's only one type of bond or two types of bonds. Carbon-carbon bonds we know aren't polar. Carbon-hydrogen bonds are only slightly polar, and since it only has carbon and hydrogen, our bonds are probably, the bond dipoles are probably going to cancel out. So C3H8 has the lowest boiling point because it has the weakest forces, or intermolecular forces. The next one would be C2H3Cl because it has a dipole-dipole force. So there's one force that's going to make its boiling point a little bit higher. Next will be C2H5OH because it has hydrogen bonding, and our molecular compounds are always going to boil before ionic, metallic, and network solids. All of them have boiling points below 200 degrees Celsius, whereas most ionic and metallic and network solids boil at over 1,000 degrees Celsius. So molecular compounds are always going to be first on our list, and then ionic will be next, ionic or metallic. You'll never have to choose between the two. And network solids actually have the strongest forces because they consist of only covalent bonds. So that would be our list of ordering compounds in terms of increasing boiling point. And the biggest trick to these questions is just making sure you know if it's increasing or decreasing. So here we have another list, and we want to predict their state at room temperature. So we're going to go through and we're just going to see what we know. We see here I have an element, magnesium. This is the first thing that caught my eye. Elemental magnesium, it's a solid at room temperature, and it's only going to have metallic bonds. So I've already set myself with a bit of a benchmark here. Anything with stronger bonding forces than magnesium is also going to be solid at room temperature. If anything has a weaker bonding than magnesium, it might be liquid or gas at room temperature. So metallic bonds. Here I see silicon and carbon. This is going to be a network solid. So it's also going to be a solid at room temperature. And now I can go, and the rest of my compounds are molecular compounds. And so I'll see if there's any I know. And I notice that here I have C6H14. And if you take a look in your data booklet on page 5, they actually have C6H14 listed, and at room temperature it's a liquid. C8H18 is also there. It's also a liquid at room temperature. So anything with bonding less than that is going to be gaseous. And now, so we're going to go through. This is molecular. They're all molecular, all the ones that are left over. So now we'll just list the forces that are in them. Here we're going to have London dispersion. Because it's only carbons and hydrogens, it's not going to have any hydrogen bonding. It's not going to have any dipole-dipole forces. So we're done with that one. Here I see a compound that has hydroxyl groups. And so as soon as you see hydroxyl groups, especially because there's an odd number of them, what you're going to see is this has London dispersion, but it's also going to have H bonding. And because it has 3 of these groups, it can have lots of H bonding. C6H14, it's molecular, it's boring, London dispersion forces, and for this one, our other molecular compound, as soon as we see that there's at least one atom different, here we have a carbons, a bunch of hydrogens, and then we add one extra atom. So what we're going to have is this kind of odd or one slightly different bond in our compound, And this bond is going to give us our dipole-dipole force. So we're just going to list our compounds in terms of strength, and we'll make sure we have our, so we want to, by increasing boiling point, same as before, so the one with the lowest boiling point is the lowest London dispersion. This molecule, so and what we're going to do is just add up electrons. This molecule here has only London dispersion. Octane only has London dispersion. So we're going to check the electrons. Here we have 6 times, and each carbon, so let me get my periodic table out here, has 6 electrons, so 6 times 6 electrons for each carbon, plus each hydrogen only has 1, so plus 14, so we're going to have 36, 46, 50 electrons. On the other one, we have more carbons and more hydrogens, so it means we're going to have more than 50 electrons. And so the molecule with the least amount of force would be C6H14, then C8H18. Then we get our molecule with London dispersion, so C4H9Cl. Then our molecule with hydrogen bonding, C3H5OH3. Finally, we have our metal, magnesium, and then our network solid. And in terms of predicting states, we already know from our periodic table that magnesium is a solid at room temperature, which means silicon dioxide is a solid at room temperature. We know from our data chart that both of these substances are liquids. So we only have 2 substances left. And this is where we're going to use a little bit of guesswork. I'm going to predict that this one's a liquid. It might be solid. Either answer is fine as long as you predict this to be either a liquid or a solid. If you predicted this substance to be a solid, you would have to predict this one to be a solid as well, because it has more intermolecular forces. But either of those 2 choices we're predicting, so we're guessing. As long as your guess makes sense, or it can be defended, then it's okay. If you had chosen for states this one to be a solid and this one to be a liquid, well, that doesn't make sense, because this C3H5 has more intermolecular force. So that kind of answer would be a mistake. But if you had gone a liquid and then a solid, that would be okay, because you're saying, well, there's enough of that intermolecular force to make that next substance, that C3H5OH3, into a solid. So we're going to sketch the structural diagrams for C2H3Cl and C2H3I, and then we're going to predict which compound would have a higher boiling point, and then they want a reason as well. So if all you do is put the boiling point, you haven't done enough. You need to say why you think one has a higher boiling point than the other. And so we're going to sketch, I'm going to do a Lewis diagram for my first compound here, and the Lewis diagrams are going to be the same because the only difference between the 2 compounds is the halogen that's in the compound. So once we do one Lewis structure, we'll have a good idea as to the Lewis structure for the other. So we have 2 carbons plus 3 hydrogens plus a chlorine. In terms of electrons, that's going to be 2 times 4 plus 3 plus 7. So that's 10. That's 18 valence electrons. Both compounds are going to have the same number of valence electrons, because all we're doing is changing that Cl to an I for the second one. Carbons are, of course, going to be our center. And so we'll build a Lewis diagram for the first one. Carbon and carbon bonded together. 3 hydrogens and a chlorine. And then we add our bonds and place the rest of our electrons. 1 here, 1 here, and 1 in each of the chlorine orbitals. We know that chlorine came with full orbitals, so we'll put the other 3 here, and there's our 18 electrons. We can see that the carbons aren't happy yet, so they're going to form a double bond. And so what we're going to end up with is something like this. And what we can see is that each of our carbon centers is an AX3 center, so it's going to be trigonal planar. And so our structure diagrams are going to be like this for 1, and this for the other one. And I could have put that I and that Cl anywhere, it wouldn't have made a difference. So now we're going to say which one would have the higher boiling point. They're both molecular compounds, and they're both very similar in shape. They're exactly the same shape. So the only thing that's different is one has a carbon-chlorine bond, and one has a carbon-iodine bond. And so the first thing we're going to do is see if either of them is polar. So the difference in electronegativity for carbon and chlorine is 2.6 and 3.2. So 2.6 minus 3.2, 0.6. If we look at the difference in electronegativity between carbon and iodine, we get 2.6 minus, and iodine is 2.7. So 0.1. This bond is polar. This bond is nonpolar. And so what that means is, since this is the polar bond, this molecule is going to have a higher boiling point. The other thing we can check is the number of electrons. And for our first compound, we would have, if we just look at the chlorine, chlorine has 17 electrons, and we're just going to find the difference between the two. The number of electrons on iodine, since these two atoms are the only different atoms in the whole molecule, the number of electrons on iodine is 53, which means iodine has 36 more electrons, and so it's going to have a higher London dispersion force because it has more electrons. And so here we have a bit of a choice to make. Dipole-dipole forces are stronger than London dispersion forces, but in this case we have a big difference in the number of electrons, 36 electrons more in this compound. So when we do our prediction, it's not enough just to say which one is right. A reasonable person could predict either of these as having a higher boiling point. What makes this question important, or what this question is actually testing, is you understanding why. So here's what I'm going to say. I'm going to say C2H3Cl has a higher boiling point because it is a polar molecule. C2H3I is not polar. And that would be a reasonable answer with a good reason for your choice. You could choose the other way too. You could choose that you might think that because this London dispersion is so much higher, because it has so many more electrons, you might choose this as having the higher boiling point. But you would say that C2H3I has a higher boiling point because its London dispersion is much higher than C2H3Cl. And that would also be a reasonable answer. So here we have two molecules, phenol and iodobenzene, with boiling points that are fairly close together. And we're going to talk about the type of bonds or intermolecular forces in each substance. And then we're going to explain why it's so hard to tell the difference between boiling points. So, if we take a look, both molecules have, and so here's where we just, it's a sentence or short answer kind of question. Each molecule has London dispersion force. They just want a list, so London dispersion force, and that's about where it ends. We already saw that iodine carbon bonds aren't polar, carbon hydrogen bonds are only slightly polar. So in terms of polarity, C6H5I does not have dipole-dipole forces. If we take a look at phenol, phenol has this OH on it, which means it's probably going to have hydrogen bonding, and that oxygen is probably bonded to a carbon, so it's going to have dipole-dipole forces as well. So C6H5OH has both dipole-dipole forces and hydrogen bonding. So when we take a look, though, we might expect phenol to have a higher boiling point because it has those stronger forces. But what we actually see is that iodobenzene has a higher boiling point. And so the reason the boiling points are close must be because iodobenzene, so C6H5I, has a very high London dispersion force. And if we think about it, iodine has 53 electrons, so if we just add up the electrons for each one, and I'll do it off to the side here, we have 53, 53 and 5 is 58, plus another 36, so 58 plus 36, 14, 94. 94 electrons. If we look at phenol, we have 36 plus 5 plus oxygen has 8 electrons, and that hydrogen has another 1, so that's 9. So 36, 45, 50 electrons. So that would be the difference there. So it says high London dispersion force with nearly twice as many electrons as C2H5OH. And that would be a fair answer. And we might want to say, well, that this high London dispersion is equal to the dipole-dipole and hydrogen bonding in phenol. And so basically, once you double the number of electrons, you're getting into an area where the London dispersion forces of one molecule might have more attractiveness to each other than the hydrogen bonding in another molecule. But if they both had the same London dispersion, then the one with hydrogen bonding would have a higher boiling point. So now we're going to look at some of the mechanical properties. When we take a look at ionic compounds, because they're not discrete molecules, each ion is attracted to every surrounding ion. What this does is it makes ionic compounds brittle. As soon as you shift some of those ions, you end up pushing similarly charged ions beside each other, and it actually helps in breaking the crystal apart. As soon as you push down on it, or if you're able to separate it enough, you're able to force two similarly charged particles beside each other, and you do that along the whole substance, and all of a sudden you have ionic forces repelling each other or repulsing each other. So you end up actually, the ion charges actually end up helping in breaking the crystal apart. When we look at metals, metals tend to be malleable, and so when you stress them, they don't break. Instead, they bend. And the reason they bend is because when you stress them, those free-flowing electrons simply associate with new positively charged spheres, new positively charged cations. And so what you have is just a free flow of electrons keeping things together. The attractive forces are never broken, they just shift. For molecular compounds, for the molecular compounds that are solid at room temperature, they're usually very large molecules. Examples would be things like animal fat or wax. Each of these molecules is thousands of atoms in size. And they tend to be soft and easily broken. You've all felt wax, and it's because the molecules are still discrete, and the only thing that really is attracting them is that London dispersion force, which is a weak force. So the only reason they're together is because they're huge. They get those temporary dipoles forming in their molecule, and those are easily separated apart. In terms of conductivity, electric current is the flow of charge, and this is why metals are especially good at conducting electricity. They have those delocalized electrons. These delocalized electrons move around freely, and electricity is the flow of electrons. So metals are good conductors. When we look at ionic compounds, because the charges are locked up in spheres, ionic compounds don't conduct electricity. Even though they have charged spheres, all of the electrons are tied up in anions. So when they're in solid form, they don't conduct electricity, but once they're in liquid form, or if they're in ionic form, in other words, if they're dissolved in water, they do conduct electricity, because when they melt or when they dissolve, those charged particles start to separate. And since they're not being held together, they can actually aid in the flow of charge. Molecular compounds, on the other hand, are never conductive. Non-polar compounds aren't charged, so they wouldn't be attracted to charged electrodes anyways. Polar compounds will be attracted to the electrodes, but remember, polar compounds have unevenly shared electrons, but their electrons are still being shared, so they're not going to leave that molecule to go onto the electrode. So polar compounds won't conduct electricity regardless of whether or not they're polar or not polar. So when we talk about electron mobility, we can compare something like sodium metal to sodium chloride. And when we compare the two in terms of current, we can say that, well, sodium solid has metallic bonds where electrons can flow freely. Also, in metallic bonds, metals have a low electronegativity. Sodium's is 0.9. This means that they are not attracted to valence electrons. Sodium chloride has ionic bonds and the valence electrons are in chloride ions. So those chloride ions have actually stolen the electrons. And remember, chlorine has a high electronegativity. It's 3.2. And this means so the electrons won't feel like flow or pass down the current. So for homework, assignment 2, once you get that done and marked, you can give the Chapter 2 test a try. And after that, we'll be moving on to the next unit, which is studying the behavior and the qualities of gases.